Now, this article, this problem in fact comes from an article that was published recently in Chemical Engineering and Technology. I was a reviewer for this paper, so I got a pre-look at this paper, so I took up the problem from there. Now, the authors in this paper, they consider the effects of 4 factors on the conversion of a reactant and selectivity to a desired product, because conversion alone is not important, or that is not sufficient. The reactant must convert to something that you want, because many reactions produce multiple products, and out of those products only some of them are useful for the purpose at hand, or only that product has a higher economical value in the market. So you want to manufacture those products more, and you want to minimize the byproducts. So basically you are looking for maximizing conversion. You are also looking for maximizing the selectivity to the desired product. So in this particular study, those 2 variables are the output variables. You want to maximize both. The input factors that the authors considered are listed there. Time of the reaction is one variable. Temperature of the reactor is the second variable, x2. Then they have 2 mole ratios, which are denoted by x3 and x4. So what happens is, in an experimental campaign, the authors would vary this according to a design, certain design. That's what is called design of experiments. So they would vary those 4 variables systematically, and what they would do is they would collect the data. You will see the data in the next slide, and using the data they will try to set up a model. Again, the model can be a single model relating this x1, x2, x3, x4 to both y1 and y2 simultaneously, or the model can be set up in as 2 different models. One model relating the x variables to the y1 variable, another model linking the x variables to the y2 variable. Both these options are possible. We will do this latter kind of strategy, and in specific I will demonstrate how the model is set up between the x variables and the y1 variable. Alright, so you can take it further later on. So what I am going to do is I am going to set up y1 as a function of x1, x2, x3, x4, the interaction factors x1, x2, x1, x3, x1, x4, x2, x3, x2, x4, x3, x4, and perhaps the quadratic terms x1 squared, x2 squared, x3 squared, x4 squared. I will take this process through the stepwise regression tool in Matlab, and that tool will tell me, out of these possible input variables that I listed, the linear terms, the interaction terms, and the quadratic terms, the tool will tell me which variables are important, alright, which terms are important in the model, and therefore I will use that to get a model for y1. I will repeat the process for y2, and when I have the 2 models, what I can do is I can use optimization tools in Matlab, which we will see in one other session how to solve such problems. Alright, but anyway, I will use the 2 models and a tool in Matlab, or I can use analytical tools, taking partial derivatives and setting them equal to 0 and so on, that we used to do in undergraduate class, or in sometimes even in high school, and then we can find out the optimal values of x1, x2, x3 and x4. So that's the goal of these people. What is the optimal value of the input variables that will lead to maximization of the phenol conversion and the maximization of selectivity to the desired product? Alright, so in the next slide you will see that we have a data on from 27 experimental runs. So we have 27 samples, the data are all given there, and then the idea is to make a model out of it. Now, as I mentioned in the class, the input variables are often coded. So in the next table, if you see a value for 0, a value of 0 for x1, which is time, it actually means 250 minutes of reaction time. If you see a value of -1 for the temperature x2, it means the temperature is set at 50 degrees Celsius in the reactor. If you see a value of +1 for x3, it means that the phenol to tert-butanol mole ratio is actually 3, and so on. Okay, so you understand that the x variables are usually denoted by coded variables. They will be coded. The response variables y1 and y2 are given usually in raw form. Okay, so those will be denoted as continuous variables, the measurements that come to you. So this is what we see in this slide. You can see those 27 runs listed there, and the coded variables for x1, x2, x3, x4 for each of the experimental settings, for each of the experimental runs, are given in the first in the columns 2, 3, 4 and 5. Okay, so x1, x2, x3 and x4. So in the first experiment, x1 and x2 are set at low values, and x3 and x4 are set at the nominal values or the middle values, because they carry a value 0. So the reaction time is kept at 20 minutes, the reaction temperature is kept at 50 degrees Celsius, and you can see the phenol to third butanol mole ratio and the catalyst to phenol ratio, those are kept at values like 2 and 1.25 respectively, because they are 0 in this first experimental run. And when this experiment was conducted, the conversion of phenol was 27.3 degrees, 27.3% rather, and the selectivity was 52.5. So if you look at the last experiment, for example, all the variables x1, x2, x3, x4 are set at their nominal values or at their central values, alright, which would denote 250 minutes of reaction time, 70 degrees Celsius for the reactor, and the mole ratios being 2 and 1.25 respectively. This experimental setting yields a conversion of 79.9% and a selectivity of 59.1%. So basically this is the kind of data that we have, alright, and the goal would be to use this data to construct a model and do optimization of the model, and then find out what conditions really maximize, in this particular case, maximize the conversion and the selectivity. And basically you would take those values and do experiments again in the lab to confirm. These are called confirmatory experiments. So you would confirm that indeed the settings that you found out through optimization really gives a very high value for conversion and a high value for selectivity. Alright, so basically that's the issue overall. The data has been provided to you also in a Matlab data file, cetdata.mat, which you would be able to download from the IVLE, and that's what I'll be using in my Matlab demonstration. Alright, so let me go ahead. I'll just jump the demonstration for now. I'll show it later, but as you can see, this is what the Matlab session that I do will look like. So let me go through it code line by line. What I'm going to do is I'm going to just clear the workspace, and I'm going to use CLC command to scroll up to the top of the Matlab window. I'm just going to clear the command window and go to the top of that. So those are the first two lines, and then what I'm doing is I'm loading the data file. So as you know, the data is available in the file cetdata.mat. So I'm just going to say load cet data, and what happens is when I load it, I will get a matrix containing 27 rows corresponding to the 27 experiments, and you will see these variables x1, x2, x3, x4, y1 and y2 in the workspace. Now basically, if you are really doing this as a real scientific investigation, you will not use all the 27 data samples for model fitting. As I said in the class, and as you know, even if you are not in my class, you would know that you have to use those 27 experiments for both model fitting and to show validation. So typically, if I were to do this, what I would do is I would randomly select, let's say 5 to 6 samples here, about 20-25% of the samples for validation. So I'll randomly pick some samples for validation, and the remaining I will use for the training. Okay, so that is what I would do, and I would construct the model once I'm using the training set, and once that model is good in my opinion, what I'll do is I will try to take that model and validate it on the validation data and convince myself that the model is reliable and can be used for further decision making purposes. But here I'm just going to take all the 27 sample points, and I'm going to just show how model is fitted using the Stepwise tool. Alright, but in a real scientific investigation you would not do that. So if you pick up this problem for your portfolio work, you should split the data into training data and test data, and then use the training data for model fitting, and then you use the test data or the validation data for validating the model, and so on. Okay, So that is one thing I am not doing here. I am just going to take all the samples and I am going to make the model. The other thing, as I told you before, I am just going to demonstrate model building between the x variables and y1. You may have to repeat the same thing for y2. Alright, again using test data, training data, etc., etc. Alright, and then once you have final models for y1 and y2, you use an optimization approach, either a numerical optimization or analytical optimization, and find out the best values for x1, x2, x3, x4. Alright, so anyway, what I'm doing now in the fourth line really is I am creating what is called the extended X matrix. So what I'm creating is a new matrix X that contains x1, x2, x3, x4 as the first columns. Can you see that? I say X is equal to open brackets. The brackets is the kind of the ones that we will use for declaring vectors and matrices in Matlab, so-called square brackets. So square brackets open, x1 space x2 space x3 space x4. Then I'm going to include the interaction variables. So after x4 there is a space, and then I will say x1 dot star x2, because I want to do element by element multiplication of the recordings x1 and x2. So I'll take first element of x1 and multiply it with the first element of x2, second element of x1 with the second element of x2, 27th element of x1 with 27th element of x2. So to ensure that this interaction variable is created properly, I'm just doing x1 dot star x2. So it is element by element multiplication of x1 and x2 that creates the interaction variable x1, x2. Similarly, if you look at the other entries there till x3, x4, you see x3 dot star x4. That creates the interaction variable between x3 and x4. Then I want to create the quadratic terms corresponding to x1 squared, x2 squared, x3 squared, and x4 squared. So the last four columns of x correspond to that. x1 dot power 2, x2 dot power 2, x3 dot power 2, x4 dot power 2. And then I use the square brackets, semicolon, to close that statement. So now, originally you had four x variables, x1, x2, x3, x4. I am interested in creating the interaction variables and the quadratic terms to create this extended X space or the extended X matrix. Because really, I may not expect that y1 is only a linear function of x1, x2, x3, and x4. I expect the interaction terms to play a role. I also expect the quadratic terms to play a role. Whether this is really true or not, we will see when we actually do the modeling. But my belief is that the first order interaction terms and the quadratic terms may be important in modeling y1. Therefore, to put my belief, I am creating this extended X space. I am putting my belief into the model that I am trying to build. Okay. So now I believe we have 14 variables in the extended X space. The original 4 X variables, the first 4 columns. The fifth column is x1, x2 interaction. The sixth column is x1, x3 interaction. The seventh column is x1, x4 interaction. The eighth column is x2, x3 interaction. The ninth column is x2, x4 interaction. The 10th column is x3, x4 interaction. The 11th column is the quadratic form of x1. The 12th column is the quadratic of x2. The 13th column is the quadratic of x3. And the 14th is the quadratic form of x4. So I will have 14 X variables. You must remember this labeling. You must always cross-reference to how you created this extended X matrix. Alright. So what I'm going to do is I'm going to now invoke the stepwise command in Matlab using the extended X matrix and the response variable which I'm trying to model. In this case, it's y1. So the Matlab command is stepwise ordinary brackets x comma y1 ordinary brackets close. Okay. So what really it does is it tries to build a model relating these linear interaction and quadratic terms to the y1, which is the response variable. So what we will see is at the end of the stepwise regression work, what the stepwise regression tool tells me, and I believe it is true, is that only regressors 1, 2, 3, 4, 10, 11, 12, 13 and 14 are deemed to be important. Alright, many of the first order interaction terms in this model, in the proposed model, didn't come out to be important. Only one interaction term, x3 times x4, which is variable 10 in our extended matrix, comes out to be important. The other interaction terms are not important. All the quadratic terms came out to be important. All the linear terms came out to be important. So we will see that later on. But I've just put the results in this slide. And then if I read off from the stepwise tool, I will see that the model is as indicated there. Y is equal to 77.9. In fact, I have to say y1 is equal to. Okay, but anyway, since we consider only one y here, I will just say y is equal to 77.9 plus 21.7333 x1 and so on. Okay, you see only the interaction term x3 x4 comes out to be important, and therefore it is there in the model. All the quadratic terms are also important in the model. You can see that. And then what I do in the remaining 4 lines of the code is I'm just trying to show you the fit that I get from the model. Alright, the regression tool, the stepwise regression tool, is not able to show that as of now. So what I do is I take the coefficients of the model, I set up this regression vector. If you see, the regression vector is nothing but the coefficients of x1, x2, x3, x4, x3, x4, x1 squared, x2 squared, x3 squared and x4 squared that I got from the tool. So I've just taken that and created this regression vector, and what I'm doing is I am trying to take those elements from x, those columns from x, multiply those columns with the regression vector. So when I say x colon comma the regressor variables, the regressor variable list is exactly what comes out from the stepwise tool. Only those columns are important from the extended X matrix. So x colon comma that vector means from all rows. The colon stands for all rows of x. That means take all the 27 samples, but only those variables that appear in those columns, and multiply this x with the regression vector, add the intercept term of 77.9 to it. That gives me the fitted values for y. And then I want to plot the experimental values, the actual experimental values on the x dimension, which is y1. These are the experimental values. On the y-axis, I want to show what is the value fitted by the model for that variable, and I want to indicate the plot by using red circles as labels or markers, if you like. And then I will just annotate the x-axis and the y-axis, saying it is the actual y1 for x, which means the experimental values for y1. The model fitted values are in y-axis, therefore I label the y-axis as fitted values of y1. Alright, so this is the procedure we will go through. So this is the model I'm trying to tell you is good for y1. A similar model has to be obtained for y2 as well. Please note, I mentioned already, you have to split the data into training data, test data and so on, and show how the model validates on the validation data or the test data. Okay, that is something you have to do. But once you get the 2 models, then you can use the 2 models for optimization purposes. Now this is how the stepwise regression tool will look like. I will show it to you later on as a live demonstration, but what you can see here is a nice GUI. Okay, nice GUI, and you will see that on the very right hand side there is a guidance tool. It tells you which term to bring in the model, which terms not to bring into the model, etc. We will see that. And then what you see as these dots with those horizontal lines going through it, the dots, the circles there that you see, the solid circles, indicate the point estimates of the parameters. The extent of the horizontal line indicates basically the confidence interval, the 90 and 95% confidence interval. You can see basically if you look at it very carefully, let's say what you see for x1 there, x1 is centered around 21.7333. That is what you see in the coefficient column, slightly to your right. Okay, so the circle there, the blue circle, solid circle that you see there for x1 is centered at 21.7333, and the confidence interval extends. You will see a blue line, thick line, and also you will see a black line, and you will see that the black line, the horizontal line, is slightly longer than the blue line. So the blue lines are 90% confidence intervals, the black ones are the 95% confidence intervals, and therefore they are slightly wider. Some of the variables you will see are in blue color, some of them are in red color. The ones in red color means that they do not come into the model. That means the tool has said that those terms in the model are not significant. So the ones in the red are those that are out of the model. They don't come into the model. The ones you see in blue color are the terms or variables that are in the model. Okay, so that's a nice distinction that you can see there. And you also see some statistics there. You see the coefficient values. For the variables that are included in the model, you will see them in blue color, like 21.7333, 5.025, etc. The ones in red we should not bother about because those terms don't come into the model. On the very right, you will see p-values associated with those coefficients. Basically, it does hypothesis testing whether that parameter is significant, statistically significant from the value 0. So if a parameter is statistically different from 0, then that means that that parameter is statistically significant. That means it is not like 0. Therefore, it can be included in the model. And if it is not statistically equal to 0, that means it is statistically different from 0. It means that the value of the parameter will be on the very right or the very left of the distribution, depending on whether the parameter takes a positive value or a negative value. So if the parameter value, estimated value, is in the tail of the distribution, very much on the tail of the distribution, it means it is not like 0. That means that parameter is statistically significant. And if the parameter value is to the extreme right or to the extreme left of the statistical distribution, the p-value will be small. What is the p-value? P-value is the area to the right of the parameter value in the statistical distribution, or the area to the left of the parameter value in the statistical distribution. Alright, so if the area to the right or to the left is very, very small, how small is small? We will consider 0.05. Anything less than 0.05 to be small, and anything bigger than 0.05 to be large. So if the area to the right, that means if the p-value is lesser than 0.05, it means that the parameter is very much different from 0, and therefore that parameter is significant. If the p-value is large, which means the area to the right of the estimated parameter value in the statistical distribution is larger than 0.05, it means that the parameter value is more towards the center of the distribution, and therefore it is like 0, and therefore it is not significant to be included in the model. So if you look at it, if you look at the last column, you will see the p-values for all the terms that are included in the model. You will see that the p-value is very small. Very small means smaller than 0.05 definitely. You can check that out. And for variables which have been left out of that model, x5, x6, x7, x8, x9, those 5 variables, you will see the p-value to be larger than 0.05, which means it is towards the center of the distribution. If it is towards the center of the distribution is centered at 0. So if it is towards the center of the distribution, we can say that parameter is almost like 0. Statistically it is 0. It is not exactly 0, statistically it is like 0. Alright? So that's the idea. So anything that has a p-value less than 0.05 means it is to the extreme, it is in the extremes of the distribution, which means it is different from 0, therefore it is significant, and therefore it will be included in the model. I also don't want you to be fooled by looking at values for x5. You can say x5 has a coefficient value of 3.225. How can that be close to 0? Alright, the point is, you cannot go by just the raw coefficient value. You have to look at the coefficient value. You should also look at the variance or the standard deviation of the coefficient value. And when you standardize it, then you have to see whether it is in the center of the distribution or at the extreme of the distribution. So the raw coefficient values that you see in the first column there, that is not an indicator of whether it is 0 or close to 0 or far from 0. Okay? So the coefficient that you see in the first column has to be standardized, and the standardized parameter has to be located in a statistical distribution, and you have to see the p-value associated with that standardized coefficient value. And then you make a decision based on whether that is greater than 0.05 or less than 0.05. Less than 0.05 means it is in the extreme of the distribution, therefore it is statistically significant. Okay, so that is the idea. And in the middle column you will see what is called a t-stat. Now this t-stat is related to the p-value also. Once you know the t-statistics, which is something like the standardized regression coefficient, then you can locate in the t distribution, you can locate that value that you see in the t stat, and then you can compute the p value. Alright, so in a nutshell, the coefficient value is given in the first column. You standardize that based on the mean being 0 and the computed standard deviation for the coefficient. Then you will get the t statistic, which is the t value associated with that, the observed t values, so to say. You take this t stat values that are indicated in the second column, go to a t table. In statistics books there is something called a t table. You can go to the t table, look at appropriate degrees of freedom, and then locate where the observed t value falls in that statistical distribution, and you compute its p value. That's what is shown in the third column. And if that p value is smaller than 0.05, you conclude, yes, this standardized regression coefficient is very much away from the center of the distribution, which means this term is statistically significant, and so on. Okay, so that is what is the meaning of those three columns that you see there. Now the intercept value means the constant term in the model, in the regression model, that will be indicated here. Remember, our extended X matrix does not contain a column of ones to compute the intercept. Okay, so basically the intercept value will come out separately, which in this case happens to be 77.9. And what other things you see is the RMSE value, root mean square error value. Now, error is what is the actual experimental value for a corresponding experiment. Let's say for experiment 1, the experimental value is something. Now the model fitted value will be something. The difference between these two is what is called the error, and you can square that error. And you can do it not only for the first experimental run, you can do it for all the 27 experimental runs here. So the experimental value minus the model predicted value or the model fitted value, you subtract, that's the error. And what you should not do is just say, I will try to minimize the total error in the 27 experiments. That's not a good idea, because bigger errors in one experiment can compensate for smaller errors in the other experiment, leading you to believe that you've got a good model. Because these errors will sometimes be positive. The experimental values will be bigger than the model fitted values. In another case, the experimental value may be smaller than the model fitted values. So if you just look at the errors and try to minimize the total error, what will happen is a bigger positive error will compensate for a bigger negative error. And therefore, when I say bigger, I mean the magnitude. So an error of 27 will compensate an error of minus 27, giving you a value of 0 for the overall error. And then you may think, oh, we have got a fantastic model with very low error. So usually the errors are not minimized in that absolute, in that sense, using the magnitudes. What they do is, you can either take the absolute values of the errors and you try to minimize the sum of absolute values. That's one thing. But oftentimes, for good mathematical reasons, what people do is they square the errors. Alright, because error, whether it is negative or positive, you can square the error and then it will become positive. Alright, so there is no compensation for positive errors with negative errors there once you square the errors and add them up. So you square the errors for the 27 experiments and you add them up, you will get what is called the sum of squared errors. And then you take the sum and you divide by the number of experiments, you will get the mean squared error. That means the sum of squared errors divided by the number of experiments will give you the mean squared error. And if you take the square root of the mean squared error, that is what is called the root mean squared error, which is RMSE. And obviously you would like to minimize that. You would like this RMSE to be as small as possible. Alright. For example, here for the model that has been taken, we get a RMSE value of 6.3. Now if you look at the Y1 column, most of the values are about 50, 60, 70 like that. So let's say the average value of Y1 in the experimental runs is about 60. 6.3, which is RMSE, is about 10% of that. So it seems like it is okay. Do you understand? If the RMSE was like 30 compared to an average Y1 value of 60 is not a good thing. Do you understand? So RMSE value, which is about 10%, 5% of the average Y values, is often seen as a good sign. Okay, this tool also shows you the RMSE values, how it evolves You can see that graphical image at the bottom. You will see it in the live demonstration as well. So when I start off and I include the first term in the model, the RMSE value is about 25 something. Now when I include the second term, it falls from 25 to about 20, and then it falls, when I include another term, it falls to about 17 something, let's say, and so on. And when I complete the model, basically what happens is when I include 10 terms in the model, alright, what happens is, that means the ninth term plus the intercept term, that's why it comes out to 10. So when I start off, the run 1 is basically only the intercept is there. There is no x term of any kind in the model. That is model 1. That RMSE is about 25. And then I include first x variable. Then I get model 2, which is an RMSE value of about 20. And after including the 9 terms that you see as blue things in the picture above, and not necessarily in that order, you will see that later, but in some order, in some good order, what happens is the RMSE value continuously falls down. Alright? So basically the RMSE is also shown graphically, and you can see the big gains are made when we include the first few terms. Then the gains are somewhat less, but nevertheless there is a gain. Okay? So that is something that I want you to observe. Now there are other two terms that I want to talk about. One is the R squared. R squared basically gives you an indication of the model fit. So the more terms you include in the model, the R squared value will keep on increasing monotonically. So whether a variable is good or whether a variable is bad, it doesn't matter. When I say variable is bad, it means whether it adds to the predictive capability of y1, it is immaterial as far as R squared is concerned. R squared is a nice fellow. Anybody it includes in the model, it feels happy, it goes up, the value goes up. Alright, so that's one thing about R squared. So people who know modeling well, they will not be fascinated by the value of R squared, because as you increase the model complexity by including new terms in your model, what happens is this R squared value keeps going up without ever indicating whether the capability of the model to predict new values for y1, when you change x values to a different setting, it will predict new values for y1. That's what is part of validation. Alright, so R squared does not give us an indication whether this validation will indeed has indeed taken place. It just memorizes. So R squared, you can say, is something that shows the memorization capability of the model, not its generalization capabilities. Alright, so R squared is something that people always record, but you have to pay attention to what is called adjusted R squared that you see next to it. This adjusted R squared is basically like R squared, but it compensates for model complexity, and it has this nice property that if you include a term or a variable in the model that is not good for predictive capability, what it does is the R squared adjusted value, the adjusted R squared value will indeed go down. So unlike R squared, adjusted R squared is not a monotonic function. If the included variable is good, its value will increase, adjusted R squared will increase. If the included variable does not play any role in model prediction, in the predictive capabilities of the model, the adjusted R squared value will actually go down. So this adjusted R squared gives an indication whether the model is good for prediction, whether the model is more complex than is necessary. All these factors are indicated by adjusted R squared. So that is something that we should carefully note. Of course, we are happy with high values of R squared and high values of adjusted R squared. Alright, but pay more attention to adjusted R squared. If adjusted R squared increases significantly by inclusion of a variable, yes, that variable should be included. Alright, so I hope you get the idea. And industrially, what we will see is that always adjusted R squared will be lower than R squared. Okay, that's something that you must understand because of the nature of the definitions, which we will see in the other presentation later on linear regression. You can see the actual formulae for R squared and R squared adjusted. So by its very construction, adjusted R squared will have a lower value than R squared. But what we need to see is the difference between R squared and R squared adjusted should not be more than 0.2. That's for industrial data. I've worked on a number of industrial problems, and this is one thumb rule that we notice. Because we know that adjusted R squared will be smaller than R squared. But we do not want adjusted R squared to be very, very low compared to R squared. Which means if adjusted R squared is too low, then I am not finding the model to be very reliable. So either I have to include other terms in the model, or go for really some non-linear model as opposed to just linear in parameters type of model. I may have to go for a non-linear regression model, or I may have to even do more experiments and so on. Alright, so just remember that the notion of R squared and R squared adjusted. Here, for example, the R squared is about 0.96 and adjusted R squared is about 0.94. Okay, somewhat very high values. You may not see this in many industrial data sets, this kind of R squared and R squared adjusted values, simply because industrial data is noisy. Alright, and the noise level can be fairly high. So you may not be able to fit or validate so nicely as may happen in some synthetic cases. Alright, so industrial data, you are happy to get an adjusted R squared of about 0.6 and the R squared of about 0.7. And if you go to biology work, or if you go to some other kinds of processes, economics and so on, you will probably not get even as high. If you are doing education research, for example, or any kind of sociological research or things like that, R squared of 0.4, 0.5 itself, people will be quite happy. Okay, so anyway, I want to leave you there. The other thing that you will see in this GUI is basically an export button that you will see there. So if you click on that export button, the GUI, the stepwise regression GUI, will bring out the parameters, the model coefficients, the statistics, etc. It will bring it and dump it into the workspace, Matlab workspace, for you to process. So that also I will demonstrate to you a little later on. Okay, so these are the things you will see. The F statistic and the P statistic that you see in the bottom horizontal box again have the same notions that I explained for the T statistic and the P value earlier. The P value, you can see, is about 10 to the power of minus 10. E minus 10 means 10 to the power of minus 10, which is a very small value, which means you can say this model is acceptable or a good model. Alright, so it shows something about the model validity, whether the model is valid or not. So if the P value is small, again it shows that the model is significant. Alright, so this is what you will see when I do the online demonstration. I shall not be repeating many of these things. I will just take you through. Alright, the procedure. Now lastly, you remember the 2 or 3 lines of code that I had at the bottom of my file, basically to plot the actual Y values versus the model fitted Y values. Okay, so this is the output of that command. You can see the red circles that I was indicating there. You can see if it is the as expected, because you have a very high R squared value. You will expect that the fit and the experimental values, actual experimental values, they align very nicely along a line. You can see that there is a strong correlation between the experimental Y1 values and the fitted Y1 values. You would expect this, of course, and that's what you see there. Particularly you expect this because you have a high R squared value. That means the fit is good. Even there you see that one of the samples you see on the far left, in fact the first sample that you see on that plot, it's not sample 1. What I'm trying to say is it is one of the samples that you see there. The fitted Y1 value is negative. The actual Y1 value is about 10 for that. Can you see that? The bottom left. That is a very suspect sample point. Basically, I think that's an abnormal point of some kind. Maybe if I include other nonlinear terms in the model, or if I go for another kind of regression model, maybe I will not see this kind of an outlier. But that sample is suspect, at least for this particular model. The other sample points nicely align along that line that you can see there. Okay, so there are this one sample that I indicated is a little tricky one. So sometimes what we do is that one sample alone, if you see something like this, we might take it out of the analysis. So we will work this problem again with just 26 samples and not 27 samples. Alright, and then do the procedure again. So the moment you see an outlier or something, either before analysis or after analysis, you can take it out and then repeat the modeling exercise again. Okay. So what I'm going to do now is I'm going to take a look at Matlab, which I have here. So basically you can see that. So I will just say load CET data, right? CET data. So this is the first thing that I will do, and then what I do is I will just say x is equal to pretend that I've just typed it in front of you. X is equal to x1 space x2 space x3 space x4 space x1 dot star x2 space x1 dot star x3 space, and so on. Alright, so this is my extended X matrix. Now if I look into the workspace, you will see that these variables are there. When I loaded CET data, x1, x2, x3, x4, y1 and y2 got loaded, and you can see each of those variables has 27 entries. That means 27 experiments corresponding to the table that you saw. And then when I typed out that x is equal to square bracket open and then all that stuff and then square bracket close, it created this extended X matrix, 27 rows for the 27 experiments and 14 columns corresponding to the linear terms, the interaction terms and the quadratic terms. Now I am ready to call stepwise command in MATLAB. I say stepwise x comma y1. So when I do that, it opens up this graphical user interface that somebody has kindly set up for us. So I'll just blow it up a little bit. So can you see now no term has been included in the model. Alright, only the constant term has been included in the model, and the value of the constant term is 46.47. Can you see this one that on the left? 46.47. Alright, and r squared and r squared adjusted are 0. The RMSE value is about 25. That's what I said, that will be model 1. The RMSE value is shown with this blue circle also here. The graphical representation of the number you see there really. Alright, and no term has been included in the model, therefore everything is in red color. And basically if you see the right hand side, it says it gives us an indication of what would be the next step. So we will not go into the algorithm of what happens inside stepwise regression. That will take several lectures to do that. But basically what it does is it tells us at this point in time the best thing for us is to bring x1 into the model. So it says move x1 in. So I will click on next step and do move x1 in. If I want to be lazy, I can just press this all steps and then it will do everything automatically. So I will not do that. I will just go step by step to just demonstrate it. So I'll just press on next step, and what happens is it moves x1 in. So the moment it moves x1 in, you can see it is in blue color. Alright, and the RMSE value has now come from 25.3 or whatever we saw to about 20.96. So there is a significant drop in RMSE, which is good. Now what you see is the R squared and R squared adjusted are about 0.34 and 0.32 respectively. Alright, which kind of gives an idea that this is good inclusion. Inclusion of x1 is good because it increases R squared, which is not a surprise, but also it increases R squared adjusted sufficiently. So x1 term, the first term in my extended X matrix, which happens to be the variable x1, is the most important variable. So basically for maximizing conversion, the first term that's important is the time of reaction, and it's not surprising in some sense. Okay, so that has been now included in the model. Okay, so now it says move x13 in. X13 happens to be the quadratic form of x3, which is x3 squared, and you know x3 is that mole ratio. So the mole ratio squared comes out to be an important variable. So when I press next step, x13 will be included in the model, as you can see here. Can you see that x13 has now become blue color? The RMSE value has fallen from some 20 something value to about 16.5 now, and R squared adjusted and R squared have gone up. Importantly, R squared adjusted has gone up from 0.31 or something to about 0.58. Alright, so inclusion of x3 squared, which is x13 in our model, is again a very good thing to do. Alright, and now it suggests move x4 in, which is the other mole ratio. So the linear x4, right? X4 in the extended X matrix, the fourth column in the extended X matrix, the fourth column is actually x4, which is the mole ratio that is indicated in the table. So I'll just bring that in. Now R squared adjusted has gone up from about 0.56 to about 0.7. So the gain is slowing down, but nevertheless R squared adjusted has increased. Now the intercept is 57.98 in this model. If you stop the model here, the model would be 57.98 plus 21.7333 x1 plus 13.55 x4 minus 25.8883 x13, and x13 is actually x3 squared. So the model at this stage is 57.98. Sorry, I'll just backtrack a bit. The model at this stage is y1 is equal to, or conversion is equal to 57.98 plus 21.73 times x1 plus 13.55 times x4 minus 25.88 times x3 squared. Okay, so that will be the model as of now. So next I will go through these steps and see, if I include x3, what happens is R squared adjusted increases from about 0.71 to 0.78 or 0.79. So again it's a good thing, and so on. I'll move x11 in, RMSE value falls down, R squared adjusted increases from 0.79 to 0.83 roughly, so the gains are getting smaller. Then it is asking me to move x14 in, then move x12 in, then it says move x2 in, which is the reaction temperature. Okay, so all this have been moved in. Then it says move x10 into the model. So I do that, and now at this point it says move no more terms, move no other terms, stop here. Because if I'm going to include any other term, you can experiment this and see, if I include any other term, the adjusted R squared value will indeed start coming down. So when it says move no terms, I'm happy. Now if I wanted to, I can say, oh, this RMSE curve, the trajectory is flattening. In fact, I can stop at this model 8. I think I don't have to include the last 3 terms that it asked me to include. Do you understand? So I can always go back and choose a more simpler model if I wanted to. So we don't have to go exactly by what this stepwise regression tool has told us. Alright? It is going very mathematically and so on. Now as an engineer, you have to take the help of mathematics and statistics, but you have to put your decision making into it, because sometimes the operators and people don't like to see a complex model. They want to see a compact model that works well. So by dropping off the 3 terms that stepwise regression suggested for us, if you are able to get a simpler model without loss of predictive capability, then you should go for that. Okay, but in this case, let us just accept that. So let's assume that this is the final model. Let me just read it out for you. The model as of now is 77.9 plus 21.73 x1 plus 5.02 times x2 minus 10.49 times x3 plus 13.55 times x4 minus 8.42 times x10 minus 15.62 times x11 minus 8.21 times x12 minus 33.36 times x13 minus 13.52 times x14. That would be the model. Alright, that's what you saw on the PowerPoint slide as well. Now I can use this export feature in Matlab. I'll click on that, and then it gives me this kind of it didn't come out fully blown when I did that, but basically it can dump the coefficients as variable beta. It can dump the confidence intervals as variable beta ci, the terms that are included in the model as variable in, the variables that are not in the model in the variable out. It can give us some statistics, it can give a coefficient table, it can give us an history of models. Remember, we went through about 10 models, so it can give us an history and so on. So basically what is going to be useful, all of this can be useful for anybody, but what I'm just going to say is, okay, dump all the variables in the workspace. So I just type OK. Now because this modeling effort is closed, maybe I'll just minimize this window And then now if I go to Matlab command window and type whos, basically it shows us, can you see that? It shows us all the variables from the stepwise regression, beta, beta ci and so on. So if I type in, for example, it will show which of the columns in the extended X matrix are included in the model. And as we know, variable 1, variable 2, variable 3, variable 4, variables 10, 11, 12, 13, 14 were included in the model. If I type out, it will show the columns of X, the extended X matrix that were not included in the model. Okay. Now if I want to see the confidence interval, you can see either from the graph or you can ask it to plot this matrix. So beta ci contains the lower confidence interval. Beta ci, the second column, contains the upper confidence interval. Alright, because the confidence interval are the point estimates plus or minus something, right? So the minus something will come in the first column of beta ci. That's why what I mean by the lower confidence interval. The second column of beta ci will contain the higher end of the confidence interval, and beta will contain the point estimates. So beta ci colon comma 1, this colon here indicates all rows, alright, and 1 indicates the first column of beta ci. Beta is the parameter estimate, and beta ci colon comma 2 indicates the second column of the confidence interval, which contains the upper limits. So if I press enter here, you can see this. For variables that are not included in the model, you can see them indicated as 0. But for other terms, you can see the left column, the left value. Let's take x1. The point estimate is 21.7333. The lower confidence interval is 17.87, and the upper confidence interval is 25.6, for example. Alright, so since the lower confidence interval and the upper end of the confidence interval have the same sign, this parameter is deemed to be statistically significant. In fact, that is why it was included in the model in the first place. If you look at x3, the third one, right? If you look at x3, the third one, the point estimate is minus 10.49. The lower confidence interval for that parameter associated with x3 is minus 14.36. The upper confidence interval is minus 6.62. So the effect of x3, which is the mole ratio, on conversion is actually a negative effect. Alright, it's a negative effect. That's why the coefficient comes out to be negative. Alright, but the confidence intervals, upper and lower, are both negative, which means statistically we are sure that the variable x3 has a negative effect on conversion. But we have to be careful, because x3 comes as a quadratic term here, alright. It may also come as an interaction term. So in general we have to be very careful when we interpret that. The linear term may suggest one's effect of a positive effect on certain y, not in this problem. In general I am saying x3 as a variable by itself can have a positive effect on y, a response variable. But x3 in interacting with something, or x3 quadratic or cubic, can have quite the opposite effect, and the overall effect is a balance or summation or whatever of all of those effects from all the terms that are there in the model. So interpreting the term separately, I am saying this, that variable x3 has a negative effect on the conversion. Alright, so if you look at the quadratic term x4 squared, the point estimate of the coefficient for x4 squared is minus 13.52. The upper end of the confidence interval is minus 7.72. The lower end is minus 19.32. So again, the variable x4 squared has a negative effect on y2. Alright, so I hope you get this. And if you look at these point estimates are the ones that I have taken and shown to you in this particular last lines there. You know, can I say, see, after this regressors, all those things that I have shown there in the comment lines as well as in the programming, they are basically values taken from the point estimates. Alright, and then I have shown this. So basically this file I will also make it available to you. So what I am going to make available to you online is the CET data, and then I will also show this file to you so that you if you want, you can read it carefully and get some practice and see whether what I have said there makes sense. Of course, you should be exploring things on your own, Please note I have put a pause command after this thing. So when you run that file that I'm going to send to you, M file, what will happen is it will execute the few lines. It will do the stepwise thing for you. So it will open up the GUI and then you can go click and make your model. And after you have completed that model, please come to the Matlab command window and press any key so that the rest of the lines will be executed. Otherwise it will just be pausing there for your input. So after you complete your stepwise regression work, then you come to the Matlab command window and then you pause it. Alright, and then the rest of the lines will be executed. Let me just demonstrate that to you for the first time so that you know. So what I am going to do here is I am going to close this window. This is the file I am going to send to you, stepwise demo.m. This is the file I am going to be sending it to you. So when I execute it, the workspace will be cleared and all that stuff. Okay, so let me execute it. So press this button to execute. So it opens up this one. You understand? So I'm just going to be lazy here and I'm just going to say all steps. Alright, and then I'll just say export and then I'll export everything to the workspace. Then I'll go to the Matlab workspace and then you see it is pausing. Can you see in the bottom it says paused? Press any key. So I'll go and press some key. Then it will go and execute the remaining lines in the stepwise demo.m file. So it will do this fitting calculation and then it will show you that result on a plot that you see there. Okay, so let me leave you here with this one, and I want to really thank you for your attention.